the presentation gave me putting emphasis on the variation of transitional functions. And the previous work, we established a multi-scale particular practical growth model, and have done some work related to the practical growth less history. And now this part we're going to focus on the transitional function variation. Okay. Firstly, the approach we're going to take is the fractional mechanics approach. And if we talk about the fatigue, and there are two approaches mainly in this field. The one is the traditional mechanics, which means we are seeking for appropriate variables in the framework of continuum mechanics. Actually, it's crack-free, and in the materials, components, or structures. And the other aspect of this approach is fractal mechanics. We pretty much are looking for fractal parameters for fractal growth laws, and residual life estimations in materials, components, and structures. Actually, we assume there is a crack in the materials or structures. And we have these two aspects, and the current work is in the framework of fractal mechanics. So we are also taking the strategy of multiscale. The multiscale is very popular concept we are borrowing. Actually, the concept we are trying to use is we're trying to divide the spatial and the temporal, the space and the time into different scales. It's a multiscale, and in the space, and we have nano, micro, macro, and even larger scales. And we divide into several scale ranges, such as micro to macro, nano to micro, and macro to large scales. These scales are just for us to understand the intrinsic properties of material degradation and fatigue. So we have this scale segmentation and this multi-scale hierarchy proposed in this framework, and we are focusing on the scale range of micro to macro. So it's this is beyond the talk of this work. The previous work established was established a fatigue practical growth model, and this was. This actually was established by Professor C, and this model we based on this model and modify this model and try to modify some crucial parameters in this model. These models, there are several factors in this model I have to mention. Firstly, this is the restraining stress. This is applied load. This is pretty much represents the macroscopic loading, and this is the intrinsic microscopic restraining stress. And we also have this macro size and a microscopic feature size, and which consists of it's two scales in this model, and the material properties on two scales are quite different. So the following work actually follow this model, and we use this model to do some transitional works. Now, this is quite familiar. This model. It's very similar to Paris law, but I have to point out this incremental strain energy density factor is different from the incremental stress intensity factor. And we are actually, this model is based on strain energy density. And based on the strain energy density, we established this model. And also considering the multi-scale scale segmentations I just mentioned, we actually divided this four scale ranges. It's pico to nanoscale ranges, nano to macro scale ranges, and micro to macro scale range, and a macro to large scale range. And in each range, the expression of this factor, incremental SED factor, is different. It corresponds to the different stress singularity, and from top to bottom, and we have this stress singularity 1, 0.75, and 0.5, 0.5. And 0.5 is just here, macro to macro scale range, and micro to large scale range. It's 0.5 stress singularity. We use this singularity and this expression to do the to simulate the fatigue growth history. And take a look at this delta S. Delta S actually is a combination of ordinary parameters as well as the transitional functions. This sigma A is the stress amplitude, and sigma M is stands for mean stress, and A is the prep growth at each range, each scale range. But mu, sigma, and D are three different transitional functions we are using. It actually has the different expressions, and we are going to define these three transitional functions. And the three transitional functions is the ratio of the material properties, and it stands for three aspects. Firstly, material effects. Secondly, is loading effects, and last but not least, and it's geometric effects. And these three effects are very crucial in the fatigue practical growth of materials, and we define these material effects, material transition functions, and it's the ratio of macro material over microscopic materials, and the ratio is always less than 1 because of the material degradation. The value is always less than 1. And the restraining stress of the loading effects, we have these material transitional functions. It's a party load, and this is a restraining stress, the ratio of the two, and we got this, and it's always less than 1. But the geometric effect is different from the two transitional functions, and it's always bigger than 1. And it's assumption we have to make during this model, because based on the material degradation and based on the material degradation, the geometric change, and also the loading facts. So so we have these three assumptions, the assumptions of the three transitional functions, this expression, and we also define the coefficient, transitional coefficient for the three functions. That represents for the material, loading, and the geometry, the three crucial factors in the material degradation. And their values actually changes over the fatigue life cycle of a material degradation, and so we have to adjust this coefficient to make the best choice to determine this best fit of transitional coefficients for this transitional function. And what is the main challenge of this multiscale model? Because we don't know the real change trend of this transitional function. We have to make some assumptions. In the previous work, we adopt this 7075 T6 aluminum alloy, and this test data. And use this test data, we do some simulations, some work, the fatigue, and we got some interesting conclusions, results here, live here, and it's, this is the test data, and this is of the dot line is the dot line is the result from a Paris law, and the solid line is a result from this model, and we have these two different curves. And if you put the curves together with the test data, and we will find the curves derived from this model is fits more. It's quite well with the experimental data. And but in this work we didn't discuss the variation of the transitional function coefficient. 42 minutes? I'm sorry, I spent too much time there. We wanted to talk about now we have to the variation of these transitional function effects here. We take the experimental data from 2043, the range scale range micro to macro, and the variation of the material coefficient for the material transitional functions here, and we take these numbers values, and we take the linearization of this fatigue Bragg's model, and we got these figures, and it looks like the material transitional function and the loading transitional functions has little impact on the curves. So we put focus on the geometric transitional function coefficient, and here we take the numbers of these coefficients, and we take the log plot of dA over dN versus the delta S. We got the parameters, the empirical parameters of this B and M for this model. Then we get this. The green line is the test data, and the blue line is between the coefficients equal to 0.6 and the 0.2, 0.4. It looks like 0.6 fits quite well with the test data, and the 0.2 and 0.4 it's very conservative. Very conservative, so if 0.6 out of the 3 is the best one. And take a look at the crack growth rates, and we have this rate, and it's also we have this 0.6 for this. It's more close to the green line test data, and so the transitional function, this set of the transitional coefficients for the 3 transitional functions, we set to it's best for these materials to 0.5, 0.45, and 0.6. Now, the conclusions here are we mainly talk about the variation of the transitional function coefficients. So the geometric transitional coefficient has the significant influence over the fatigue crack growth behaviors. So we put emphasis on this GTF. So the choice of this cannot be too conservative, not to be too sharp. So that's my conclusion, my part. Thank you.
Thank you.